this example problem, there is a crate that is on a ramp, and this crate is going to remain stationary on the ramp throughout the entire problem. Now, the fact that the crate remains stationary tells us something about all the forces acting on the crate. If the crate is remaining stationary throughout this problem, the acceleration of the crate throughout this problem is going to be 0. And if the acceleration of the crate is 0 throughout this entire problem, that tells me that the sum of all the forces acting on the crate must also add up to 0, because F naught equals ma, and we said a is 0. Now when I say the sum of all the forces, force is a vector, so we need to add forces as vectors. We need to add the x components together, we need to add the y components together, and we're not allowed to mix them in any manner. All the x components of all the forces should equal 0, and all the y components of all the forces should also add up to 0. I want to go on a bit of a side tangent here. The crate remaining stationary is one possible example of acceleration being 0, but this is not the only possible scenario you might encounter where acceleration is 0. If you think back to when we first defined acceleration, we said acceleration is defined as a rate of change of velocity with respect to time. As long as my velocity is not changing, as long as delta v is 0, then the acceleration is going to be 0. So another possible scenario you might encounter where the acceleration is 0, what if I say there's a ball that is moving to the left with a velocity of 5 meters per second to the left? If this velocity remains constant, then the acceleration is going to be 0 because delta v is 0 in this delta v over delta t. And as long as acceleration is 0, then F naught is going to be 0 as well. So this is one common example of 0 acceleration when the forces all add up to 0, but this is not the only possible scenario where the forces on an object must all add up to 0. As long as the acceleration is 0, as long as velocity is constant, then you know you are guaranteed F naught is going to be equal to 0. So that side tangent is over. In this problem, we are told that there are several forces acting on the crate. One of the forces acting on the crate is friction. To determine the direction of friction, what I'm going to do is I'm going to ask myself, if I could magically wave a wand and turn friction off, what direction would the crate move? So I think about it. If I could turn friction off, I expect the crate to slide down the ramp. Now I know friction actually exists, and static friction is going to oppose or be opposite the direction the crate would move if I could turn it off. The crate would move down the ramp, therefore static friction must point opposite that direction. So the force of static friction will point up the ramp, something like this. So here's the force of static friction. In this problem, we only have static friction. We're not going to consider kinetic friction. So I'm not going to bother with the subscript between static and kinetic. I'll just say friction and we'll just remember I mean static. Another force acting on the crate is gravity. Gravity is fairly easy to draw in. Gravity always pulls towards the center of the Earth, unless you're next to a black hole or something else. At that point, you have bigger problems than physics examples to worry about. So the force of gravity is going to try to pull the crate down towards the center of the Earth. So here is my force of gravity. The crate is on a surface, and that crate is not falling through the surface. The crate is not falling into the ramp. That means there is a normal force. The ramp is pushing on the crate. The rule that tells us the direction of the normal force is the normal force will be perpendicular to the surface. Because I have a surface that is at an angle, basically because I have a ramp, then the normal force will be perpendicular to this angled surface. I could draw this in. So perpendicular to the angled surface is going to point perpendicular to the ramp, so something like this. I'm going to call this force F normal, Fn. And the final force we have is the force of a push. So in addition to all these other three forces Reed drew, we are told that there is a person pushing on the crate, and the person is trying to push the crate into the ramp. So the person is pushing perpendicular to the ramp and down into the ramp. So the direction of the person's push is basically opposite the normal force, based on the way the question is phrased. So I could draw the direction of the person's force on the crate to be something like this. And I will call this Fp for the force from the push. I think about this problem, I reason that we accounted for all the forces. So the next thing we're going to do is we are going to choose somewhere to place an origin and set up a coordinate system. In problems involving ramps and inclined planes, you will almost always want to set up your coordinate system so the x-axis lies along the slope of the ramp and the y-axis is perpendicular to the ramp. It is possible to solve problems with the traditional XY axes like this, but the math ends up being harder, so it's not recommended. If you want to challenge yourself after this problem, try working through this problem again in this coordinate system. It will be good practice for breaking vectors into components and keeping track of everything. But in the example on the video, I'm not going to do that. So I will have my x-axis lie perpendicular to the ramp. So the x-axis will look something like this going up the ramp. Here is my x-axis. And the y-axis will point in the same direction as the normal force. So the y-axis will be coming perpendicular out of the ramp, something like this. Now, one other thing I'm going to just mention here, in the picture that I drew, it looks like I drew the normal force and the force of the push as being the same length on the whiteboard. There is no reason to think that these two are going to be the same. I just happen to draw them with the same length of the marker. But as of right now, we do not know what the magnitude of the normal force is. We do not know what the magnitude of the force from the person pushing on the crate is. The next thing I'm going to do is, this picture is kind of busy. It's not very easy to work with. I'm going to redraw this picture. When I break vectors into components, put things in their x and y directions, I'm used to working with x being to the right and y being up. So I'm going to redraw this coordinate system in the traditional way. So I'm just going to redraw the exact same picture, but tilt it to make my math a little bit easier and a little more visually appealing to me. So here is my y-axis, and here is the x-axis of my coordinate system. I have the crate I will place at the origin. So here's the crate. It does not need to be very big in this picture. And I have four forces acting on the crate. The force of friction looks like it's entirely in the positive x direction. So here is the force of friction on the crate, F friction. There is the normal force that is entirely in the y direction. So the normal force is going to point straight up like this. Here is F normal. There is the force of the push. Now, if you remember to chapter 3 and vectors, we are allowed to take a picture with some vectors drawn on that picture. We're allowed to pick up a vector and move it around on our paper to some other location. The direction of the push is in the negative y direction, so I could, without any loss of accuracy, draw the force of the push to be something like this. So now it is more traditional to what I'm used to, where a force is kind of originating at the origin and pointing in whatever direction it points in. The next thing I'm going to do is look at gravity. These three forces were fairly easy to draw because they are entirely in the x or the y direction, positive or negative. Gravity, not so much. Gravity is in the third quadrant. So I will ask myself, what angle does gravity make with the negative x-axis? What is this angle? So I could look at the picture and I notice if I just kind of continue this line from the gravity force straight down, this will make a right triangle. So here is a right triangle. I'm just using some geometry and I know the angles of a triangle should add up to 180 degrees. So I could say if this angle is 35 degrees and this angle is 90, then this angle must be 180 minus 90 minus 35. So that angle must then be 55 degrees. So the force of gravity will be 55 degrees away from the negative x-axis. So this angle here is 55 degrees. Here is the force of gravity. And this angle I drew over here is 55 degrees. The next thing I'm going to do is I am going to try to write out every vector in its component form. So I'm going to write the acceleration in its components, the normal force, the force of friction, as much as possible. I want to write every vector in its component form. Before I actively go and write out every vector in this problem in its component form, the first thing I'm going to do is I'm going to just say something about the magnitude of every vector. So, for example, let's consider the force of gravity. The force of gravity has a magnitude of F equals mg, mass of whatever object you're talking about times the acceleration due to gravity. So the force of gravity I could write as mg. In this particular problem, we are considering a 3 kilogram crate, so m is equal to 3, and we are doing this experiment on Earth, so acceleration due to Earth's gravity is 9.8. I put that number in a calculator and I find 29.4. So what that means is this force of gravity vector that is pointing off into the third quadrant has a magnitude of 29.4. At this moment, if I were motivated, I could think back to chapter 3. I have the angle that this vector makes with the positive x-axis, 180 plus 55 more. I could break this vector down into its x and y components right now, but I want to hold off on that for a moment. What about the normal force? How should we write that? Well, I don't know what numerical value the strength of the normal force is going to be. So for the normal force, I am just going to write that as Fn. Now, whatever Fn ends up being, okay, I'll have a number for it, but I can't really go much beyond this. The same is true for the force of the push, the strength with which the person is pushing onto the crate and trying to push the crate into the ramp. For the push, I do not know how strong this force is. I'm going to write it as just Fp. Now, presumably later on in this problem, we'll go through calculations, we'll get a number for Fp. And for the force of friction, well, friction I kind of can say something about. It's not like gravity where I'll be able to get a number out, but at the same time, it's not just going to be a friction, because we know that the force of friction in this problem is going to be equal to the coefficient of static friction times the normal force, and we were given the coefficient of static friction, so I could write that as 0.3 times Fn. Now, hypothetically, if I were to be given a value for the normal force, then I could write a number for the force of friction. But at this moment, let's look at what we've done. We have a number for the force of gravity, We do not know the normal force. We do not know the force of this push. We don't know friction, but we could write friction in terms of the normal force. So if I look at what I have here, I have 4 forces, but they are written in terms of 2 unknowns. And if I want to be very thorough, I could say acceleration, because acceleration is a vector in this problem, that is just a is equal to 0 for both the x and the y directions. The magnitude of acceleration is 0. So now what I'm going to do is I am going to take the magnitudes of these forces as I wrote them, and I am now going to account for the directions, both the x and the y direction. So the force of gravity I could write as part of it is going to be in the x direction, part of it is going to be in the y direction. So the force of gravity in the x direction will be 29.4 times the cosine. Okay, I need to think about this for a moment. We have 180 degrees from the positive x-axis to the negative x-axis, plus 55 degrees more. So 180 plus 55 gives me 235 degrees. So I get 29.4 cos 235. And if I put that number in a calculator, I'll get the force of gravity in the x direction is negative 16.9. Similarly, I could do the same thing for the y direction. Cosine will be sine in this case. So the force of gravity in the y direction will be 29.4 sine of 235. When I put that in the calculator, I get the force of gravity in the y direction is going to be negative 24.1. What about the normal force? Well, we said we do not know what is the magnitude of the normal force, but we look at this picture and we see the normal force is entirely in the y direction. So I could say that the normal force in the x direction, F normal x equals 0, F normal y equals the magnitude of the normal force itself. I could do something very similar for the force of this push. So the force of the push in the x direction is 0. The force of the push in the y direction will just be negative magnitude of the force of the push. The force of the push is down in the negative direction. That's how I acquire the negative sign. And whatever the magnitude, whatever the strength of the push force is going to be is right there. Now the force of friction, I see it as entirely in the positive x direction. So I could write the force of friction in the y direction will be 0. The force of friction in the x direction is going to be 0.3 F normal. And if I want to be very thorough, I should also include acceleration. So I could write the acceleration in the x direction is equal to 0. The acceleration in the y direction is equal to 0 as well. Now, I'm going to say, notice how I wrote everything out on the board. I have 2 columns. One column is every vector in the x direction. The other column is every vector in the y direction. When I begin solving F net equals ma, I remember that Newton's second law is going to really be 2 equations. One equation, all the forces in the x direction have to add up to mass times the acceleration in the x direction. All the forces in the y direction have to add up to mass times the acceleration in the y direction. When I write out all the forces kind of in a table like I did here, I am completely done with the physics of this problem. I can just turn my brain off and just go through the motions, go through the arithmetic of this problem. I rewrote the table I just had on the board to make it a little bit neater, and I think the convenience of having the components of our vectors as much as possible written in a table, something like this, is When I work with Newton's second law, I am going to have to solve F net x equals mass times acceleration in the x direction, and I'll have the same thing for Newton's second law in the y direction. When I solve Newton's second law in the x direction, every term in the x direction for every vector is already written right here. F net is the sum of all the forces, and F net x are all written right here for me. And acceleration in the x direction is right here. At this point, I could basically turn my brain off, just go on autopilot. As long as I can copy numbers and whatever I wrote down, I'll be okay. And the same is true for the y direction. When I solve F net y equals MAY, the y component of every vector is written right here for me. So all I need to do is plug in the net forces in the y direction, which are these four, and the acceleration in the y direction, which is given to me right over there. Now, we will have two versions of Newton's second law to solve, one for the x direction and the other for the y direction. Do we go with solving the x components first or the y components first? In general, there is no rule on which you should solve first. I'll just say if you have one unknown in one direction and two unknowns in the other direction, solve for the direction that has just the one unknown first. So in this case, negative 16.900, Fn is one unknown. We only have one unknown in the x direction, so I'm going to solve F net x equals max first. In the y direction, here I have an Fn, here I have a Fp, so in the y direction I have two unknowns, so I would not be able to solve this with one equation alone. So on the right side of Newton's second law, F net x, I have four forces in the x direction. Because of the choice of coordinate system we decided to go with, two of these forces in the x direction are going to be equal to 0, and that makes my math really easy to do. So force of gravity in the x direction is negative 16.9. The normal force in the x direction is 0. The push in the x direction is 0. Friction in the x direction is 0.3 Fn. And equals to mass times acceleration. The mass of the crate is 3 kilograms. The acceleration is 0. Now, at this point, I could go through the arithmetic of this, and I get negative 16.9 plus 0.3 Fn is equal to 0. And when I go and solve for the normal force, I find that the normal force is equal to 56.3. So Fn equals 56.3 newtons. Now I know the magnitude of the normal force, and I have another piece of information that I could plug in over here. The normal force we know is that much. So I have 56.3 newtons. At this point, when I solve Newton's second law in the y direction, I only have one unknown, and this will be the force of my push. So I could set up Newton's second law in the y direction just like before. I'll have F net y equals MAY now. So the forces in the y direction, we have the force of gravity in the y direction is negative 24.1. The normal force in the y direction is 56.3. The push in the y direction minus Fp. The friction in the y direction is 0. This makes our math a little easier. Anytime you need to add or multiply by 0, that's nice to work with. And we used up all the forces for F net y equals mass times acceleration. So the mass of the crate is 3 kilograms, but again, the acceleration is 0. So at this point, I could go through the arithmetic of the problem, and I find that the force of the push on the crate is equal to 32.2 newtons. So what this problem is telling us, if I push down on the crate, the force of my push is going to contribute and tend to increase the normal force. If I push harder and harder, then the normal force is the force that prevents the crate from falling through the ramp or tunneling through the ramp. Normally, gravity is pulling the crate down into the ramp by some amount, but my push is also trying to force the crate into the ramp. The normal force has to cancel both this pull of gravity and the push. And so I could ask, well, if I completely let go of the crate, friction will not be sufficient to prevent the crate from sliding down the ramp. So what is the minimum amount I could barely push on the crate and prevent it from sliding down the ramp? And that is why this limit where we are barely keeping the crate on the ramp, that is why I set the force of static friction as an equal, and we end up with the force of the push being this much.